Thank you for the introduction, and to Martha and the organizers for the invitation to be here. So I guess I should say I'm a mathematician, and the talk I'm about to give has a very different flavor from what we've heard before, so I hope that's okay. So I want to shift a little bit and talk about natural language, and in particular mathematical structure in language, from a category theoretical perspective. So I understand that maybe not everyone in here is a category theorist. So I've designed my talk to be at a very high level. I was more interested in getting across some of the ideas rather than the formalities, so I hope that the mathematicians will forgive me. But of course, if you have questions, I'm happy to answer. So maybe just to kind of set expectations or to set the stage, let's see. What I would like to describe for you is a mathematical framework for language inspired by large language models. So, of course, by mathematical, I mean from the perspective of category theory. I'm going to tell you what that is in a little bit, but let me just first answer the question why. Like, why this perspective out of any other branch of math? And I think one answer is, number one, it's a very nice way of thinking about mathematics, but also it allows us to bring in very few assumptions to the table, which I think is a nice property to have. What do I mean in that sense? So for the next 50 minutes, don't think so much as me presenting to you a model into which I'd like to fit language, but rather we're just going to sort of look at corpora of text, or look and see what's there in language and kind of point and say, from a math perspective, this is such and such. So it's not so much a model we're fitting in, but just kind of rather seeing what's there. And I just should say this disclaimer up front. The mathematics that I will present today are sort of like a first step in this direction. So certainly there's a lot of things that we can't do yet, but it's a little bit like, here's some interesting ways that we can explore. And when I say inspired by large language models, I don't mean we're picking an LLM and then looking inside and pointing and trying to describe sort of the architecture, but rather just this curious fact that sort of in the tradition of the distributional hypothesis in linguistics by Zellick-Harris in the 50s, that the words that appear in similar contexts sort of have similar meanings. And you sort of see this with large language models because there's not, much going on. You just say, here's everything that's ever been spoken or written, and given that information, you can produce strings of coherent text. So just sort of given what knowledge about what goes with what in your language, together with the statistics of that, kind of how far can you go? So the statistics part, or the enriched part, is what I mean by enriched category theory. So this is like a richer version of category theory. So first I have to introduce category theory, then I have to introduce the sort of 2.0 version of it. And so that's where we're going. Everything I'm going to say today is based on joint work with John Tarilla, who's a mathematician at the CUNY Graduate Center, and Yannis Vlasopoulos, who's at the Athena Research Center and the IHES. This is in a paper of the same title of this talk. And then at the end, I'll share some new results. So this was from 2022. Okay, so this is kind of the overview, but now let me say some words about category theory. So here's the outline. I want to introduce this branch of math, describe for you how to think about language from this lens, and then basically just see what we can do from there. Now, what is category theory? Okay, I think if you were to ask different mathematicians, you might get different answers. So I'll just say one way I like to think of category theory, it sort of emphasizes the relationships that objects share with one another. So rather than taking a mathematical object and sort of scrutinizing it under a magnifying glass and looking at its internal anatomy, you zoom out from a bird's eye view, and you sort of ask, how does your object relate to other objects in its ambient environment? So actually, there's a theorem, which I will share a little bit with you later, that says everything you need to know about your object to distinguish it from something else is captured in its network of relationships to the objects around it. And I'm going to come back to this. But already, maybe you can see why this kind of relates to language, because this is kind of the math version of this distributional hypothesis. If you want to understand something about a word, the meaning of a word, you look at the context in which it fits in the language. So I'm going to get to that in a little bit. But I have these blobs with arrows and relationships on them, which is not too helpful. So let me just give you some concrete examples of what these things might be. These things could be sets, and a relationship between sets is just a way to get from one to another, a function. Now I'm going to make a very elementary but helpful observation, and that is if I have two functions where the source of one matches the target of the other, then I can compose them to get a third function, in this case from x to z. That's an elementary observation, but I want to make it because maybe your objects are sets, but you could also have vector spaces. Maybe x, y, and z are now finite dimensional vector spaces. And now we're thinking of a relationship between vector spaces as a linear transformation between them. It's a function that respects the linear structure. And I'm going to make the same observation again. Given two linear transformations that are composable, I can compose them and get a third map, a third arrow that is the composition of the two. So I'm just making some observations of things that are categories, and I haven't told you the definition yet because I want to give examples first. Another one, just think of real numbers. So now my objects, the things I'm interested in are numbers. I mean, they could be any real numbers, but since we mentioned probabilities earlier, let's just think of those between 0 and 1. And now I'm going to think of a relationship between numbers as the usual less than or equal to, the usual ordering on the rails. And so by transitivity, again, we have this composition rule. So there are different ways of thinking about mathematical objects and relationships between them. And the three examples we've seen can be sort of summarized in this formal definition of a category. So here's a loose definition. A category, C, consists of some objects together with arrows between them, which we call morphisms, and also a composition rule of the kind that I described on the previous slides. So if F is a morphism from X to Y and G goes from Y to Z, then I can compose them. There's a third arrow, namely their composition. And you ask that these things satisfy some reasonable axioms, which I'm not going to get into, but these are kind of the basic ingredients that I want to focus on. Okay, so this is a definition, but what does this have to do with language? So let's think of it this way. In category theory, you have objects. In language, you're dealing with strings of symbols or tokens from some finite alphabet. In category theory, we actually ask for a set of ways to get from an object X to an object Y. So we can speak about the set of morphisms from X to Y. In language, we have something similar. I'm going to now describe for you a relationship between two strings, namely substring containment. So if I have a string like blue and another one like blue marble, I'm going to draw an arrow to indicate that blue is contained in the string blue marble. So if I had another phrase here like curiosity killed the cat, then I'm not going to draw an arrow because blue is not contained in that string. So I here in language, you have a set of at most one arrow in it. Okay, just by way of notation, because this will be convenient later, in category theory, you write that set not as a picture, but as C, the name of the category of X comma Y. So whenever I write C of X comma Y, I mean the sometimes called the Ham set, the set of ways to go from X to Y, the set of arrows. Okay, well, of course, my set in language just has one arrow in it, but that arrow is somehow decorated in some sense with a probability, namely the probability that I'll see the expression blue marble given the prompt or given the prefix blue. There's a probability there. Where is it? Where do I get that probability? Let me not say for now, like let's just say intuitively there's some non-zero number associated to it, and you can think of those numbers, those are what LLMs are approximating in a sense. And in fact, I'll come back to this and make this connection tighter.
A very, very dumb question, but subset inclusion that's of course a pre-order, a partially ordered set, but you are not wanting to look at it that way here?
No, I am. This is
You
a
are,
pre-order.
okay, so you are going to be
It's a
going.
pre-order, yes.
Okay,
exactly.
okay.
Yeah. Yes.
Very dumb question. So
Sure.
a string can be included in another string in more than one way. In that case, you would draw more than one arrow.
Yeah, like if I had a string with blue 3 times in it, I'm just going to draw one. So if it is contained in there at least once, then I'll draw one. You could do more, but for now, let's just do it this way. Yeah, that's a good question. Okay, so these arrows are decorated with something like conditional probabilities. So in general, I have numbers now. In category theory, I have sets. In language, we also have sets, but we have something more. Now let me keep on with this analogy. I mentioned this composition rule in category theory. This is just a nicer way to write it. If I have a way to go from x to y and a way to go from y to z, then I can sort of combine those to get a morphism from x to z. Okay? So I'm just rewriting the composition rule in this nice way. So the question is, does language have something comparable to that? Because if so, that's very nice that we can think of language through this perspective. And I will just tell you the punchline up front. The answer is yes. However, I want to build up to that. So that's kind of like where this talk is going. I could just show you the answer now. In fact, it wouldn't be that hard. But I think to appreciate why this is so nice that we can fill in this question mark, we really have to build up to it. And that's kind of my goal for the next, I don't know how many minutes that we have left, okay? Okay, so let me just summarize what we've observed so far. Before we even include probabilities, we can think of language as a category in this pre-ordered way, like we just heard. So as we said, just to summarize, let's consider objects are strings from some finite alphabet of symbols. Think of them as expressions in language, and we're going to draw an arrow to indicate substring containment, and then you have this transitivity. And this identity, every string contains itself. That's part of the axioms I mentioned that I kind of swept under the rug, but I'm just making this observation. You can compose arrows, and so you have this nice category. Okay, so I did the first 2 things on the list. We introduced category theory.
So this is a pedantic point.
Sure.
So, your arrow from x to y was the probability of seeing a y if you've seen an x. But it doesn't quite work with the self loop because it's not like what is the probability I see another loop once I've seen a blue. So
Yeah.
It's just one. Right? It's the probability that you've seen blue, if you've seen blue, is just one.
No, I thought it's the next. So you see a sequence.
Okay. I know what you're saying. It's excellent. I'm going to get to that. So yes, we're going to handle that in about several slides from now. So if it's okay, if you can hold on to it, yeah. So we're going to define things to clarify that point. And in fact, I'm just going to I'll get to it later. Yeah, it's a good question. I know what you're asking. It's good. So we'll just postpone and come back later. And when I come back, if it's unclear, then please ask. Yeah. Okay. So now I just want to see what we can do. It feels like we haven't done much, and we really haven't. But now we just kind of want to turn the mathematical crank and see what we can get from this. So I want to share with you 6 things, at least 6 things that we can do now that we have this perspective of language as a category. There's ways to represent meanings, which I will explain what I mean in a second. There's ways to operate on those representations. This is all before we've incorporated these probabilities that we're going to unwind in a second. Once you do that using enriched category theory, then you can repeat items 1 and 2 and kind of do the richer version of that. And then at the end, I'll share with you how to change from probabilities to a more geometric perspective. So what do I mean by represent meanings? Okay, I want to go back to the perspective of the distributional theory in linguistics, where the meaning of a word is somehow captured in its context or in its environment. And this is actually going to take us back to that theorem that I mentioned at the beginning. So if you'll recall, I said there's a theorem in category theory that tells you everything you need to know about an object to distinguish it from another is somehow harnessed or contained in all of the relationships or morphisms that that object has in its ambient category. So it's like people too, right? You can learn a lot about a person by who their friends are. So you can learn about mathematical objects by who their friends are, but not just a lot, like everything you need to know. So this is actually called the Yoneda lemma. although it's a theorem, but it's called a lemma. And I think it would benefit us if I just show you a little bit of what this looks like so that we can use some of these ideas a little bit later. So remember, C of x comma y is the set of morphisms from x to y. So if I just leave that second slot blank, I'm fixing an object x, and I'm looking at all of the relationships that object has to every other object in the category, right? Such that when I fix a y, I then get a set. So this thing here on the slide tells me a way to pick an object in a category, y, and get a set out of it. It gives me a mapping from my category into the category of sets. So by thinking about relationships of objects, we have now defined a relationship between two categories. And this has a name also. It's called a functor. More technically, a functor is an assignment between objects and morphisms of one category to another that respects the categorical structure. But for now, the punchline is you can think of this C of x comma blank, which starts with an object and looks at all of its relationships, as a functor, a way to go from your category to the category of sets. This is actually called a representable functor, so it's sort of representing the object x. It's also called a co-presheaf, but a representable functor I think is intuitive because this functor contains all of the information you need to distinguish x. It's sort of like it's, what's special about this object? It's contained in this functor. And in what sense is this true? This is precisely the theorem I mentioned, or the Oneida lemma. So the statement is, or really a corollary of it, the statement is a little bit technical and doesn't look too friendly. But the upshot is, this thing that you can prove when you have all these definitions, is that two objects, x and y, are isomorphic. They're the same, essentially, if and only if the representable functors are isomorphic, are the same. Of course, you have to say, what does it mean to be isomorphic and so forth? And so there's definitions there. But here's the essence of what I was saying earlier with the picture with the blobs on the previous slide. If you want to understand something about an object, look at how it relates to all of the other objects in this category. Okay, so this feels very compatible. Oh, yes.
I'm just trying to remember from what I learned. The Oneida lemma, though, it's more, the example that you gave, I think it's called locally small.
Yes, yeah.
The Oneida lemma is more general.
That's right, yeah. So it's nice that we have a very small, we have a category that satisfies the size issues, but yeah, things get a little bit hairy, yeah. But anyway, I'm brushing a lot of details under the rug, yeah. Thank you, yeah. So translating these ideas to language, here's the idea. Given a prompt or a string or an expression x, we want to consider all of the ways it fits into the language, its context, so to speak. So we just ask, okay, is x contained in some expression y? If so, there's an arrow. If it's not, there's no arrow. So in other words, just as a concrete example, remember I'm denoting these sets by the name of the category, parentheses, string, comma, string. So for any expression x, it has its representable functor L of x comma blank. The value, when x is blue, the value of this functor on the string blue marble is the set containing an arrow. And the value of this functor on any string not containing blue is the empty set. So this is an example of the functor that represents the word blue. So just in general then, the Oneida lemma motivates us to consider representable functors associated to expressions or strings x that sort of represent the meaning in this sense that it's capturing everything that contains that expression in the language. So it's sort of the category theory version of this picture that I have. Now, that's nice. An alternative way to think about the image of this functor, you can kind of think of it as a column vector indexed by all of your strings, where there's an empty set in that entry if the string does not contain, in this case, blue. And there's just the 1-point set, the set containing an arrow, which I draws an asterisk if it does contain blue. So it's almost like a one-hot encoding, sort of. Like if you think of these as zeros and ones, it's sort of just telling you yes, no, yes, no, yes, no. Yeah.
So in this, it's just the string blue. It's not a word. It's not a concept.
Nope, just the
So
string.
like blue Christmas, blue marble, blue merle,
Yes.
dog coat, all the same.
Yes, yes.
Okay.
They would
So it's
just have
so
a
it is
string.
like it's different than like the way we would conceptualize language.
Yes.
We said like,
Yes.
is this blue the same as this blue?
Exactly, that's right. Yes, I'm not correct. These are just capturing something about strings. But the point is, somehow the difference, maybe you should be able to start thinking about it now that you have like a representation of this word blue, because it tells you all of these different contexts in which it appears. I haven't incorporated probabilities yet, but like there's a lower probability that, I say I have a blue idea, then the ocean is blue. So somehow the meaning of blue is also contained in those probabilities, which is where we're getting. And somehow that information is like sitting here, at least in just knowing where does blue fit in. So in other words, there's a little bit more semantic information in this functor representation than in just the bare bones, like is there an arrow from this one string to this other string? And I'm actually gonna get there to like, when do you start to see something like concepts, and like, can you combine them to get new concepts? That's where we're going.
Sorry, just a
Oh.
clarification. Are you assuming your category has infinitely many objects?
Yes, oh yeah, it has, yeah. It's like a free monoid, basically. Yep. Okay, so getting to this. So this segues into Erica's point. This category, strings with arrows, this preordered set, basically, does not have really any other structure to it. Like there's no way to combine things. I didn't mention anything about concatenation. There's no like algebraic structure. There's nothing that sort of gets at like a concept or maybe combining concepts to get something more sophisticated. And so you don't really want to stay there. Now, what we have done in the previous slide, we looked at a functor, a mapping from our language category into the category of sets. Sets are very nice because you can take their intersection, you can take their union, you can take quotients of sets. The category of sets has lots and lots and lots of structure. So when you look at functors valued in set, you now inherit the structure that set has. It's like if you have a set, you can't really do anything with your elements. But if you look at real valued functions on that set, now you have addition in the reals and multiplication and all sorts of stuff. So whatever you can do in the reals, you can do on functions valued in the reals. So it's the totally analogous idea here. So I want to, like, what are, in real numbers, you can add, multiply, divide, whatever. Like, what are the analogs in category theory? Okay, so I didn't have to include this slide, but I just like the picture, so I wanted to put this in here. So it turns out, like when you survey mathematicians and you ask them, if I have a whole bunch of objects, like how do I combine them to create new objects from my existing ones? And if you take a survey of mathematics, the answers sort of fall into two, I was gonna say categories, but like two chunks, yeah, like two flavors. And they have names called limits and co-limits. Now, the limit of blah, blah, blah has a very technical definition. I don't want to show it to you. But like the intuition that I kind of have, limits almost have this idea of like stacking objects on another. So if you think of like taking the Cartesian product or something, you're kind of like multiplying things together and they get bigger. So limits kind of have that feel. And co-limits is like the dual notion, and it has this almost gluey feel, like when you take the quotient of something, you're like gluing them together. This is not at all precise, and I apologize that I'm sharing this very informal way, but hopefully it gives you some intuition. And the nice thing is that when you look at the very general definition that tells you how to create new objects from existing ones, things that you're familiar with just are special cases of this more general idea. So things like intersections of sets and products, direct sums of vector spaces, meets and lattices, greatest common divisors, kernels of group homomorphisms, these are all special cases of this general concept called a limit. They have dual notions, unions, coproducts, direct sums, and so forth. These are all special cases of this more general notion in category theory called a colimit. So what I was saying, when you look at set, you can do a bunch of things with sets. These are special examples of constructions that fall into these two buckets. And so you have this at your disposal when you look at functors from your very basic language category valued into set. So here's kind of the summary. This is what I'm saying before. You can consider all functors from your language category L into set, not just the representable ones, but you can imagine there are other functors that we haven't thought about, just arbitrary functors. This entire collection itself forms a new category, a functor category. This category has lots of structure. It allows you to do the things on the previous slide. Why? Because they're functors valued in set, and you inherit the structure from that category. So the punchline is, when you kind of unwind what the definitions mean, you end up having something that feels like conjunction, like these logical operations. Conjunction, disjunction, and implication of your representable functors. So I'll give you a concrete example. Suppose I have the functor representing the word red and the one corresponding to blue. I'm going to take it's called a coproduct, which is a little bit like disjunction in the following sense. When you look at the definition, what is the coproduct of two representable functors in this way? You find you get a new functor on your category, a new way to assign text to sets. And here's what it looks like. Again, you have a column vector indexed by strings that's non-empty on the union of all strings that contain either the word red or blue or both. So it's supported on the union of strings containing red or blue or both, which matches very nicely, I think, with like the role that union plays as logical or among sets. So you can do the same thing for conjunction. It ends up being the product of the the representable functors. And implication, it's a little bit hairy, that one to work out, but you can do that, and we did it in the paper I mentioned. So this is interesting because now you can sort of combine meanings to get something that's a little bit more interesting. Maybe what's like red and blue, I don't know. Like cat or dog, maybe that's like the concept of a household pet or something. So you can start to see maybe you can combine these meaning representations to get sort of something that's representing concepts or like combinations of concepts. Again, this is very bare bones, but it's interesting just to look and see what's there. And this so far has nothing to do with probabilities. Yeah.
Excuse me, just on the previous slide. So this little, I don't know how you would call this, little flower or whatever. It used to be just an arrow, right?
Yes.
And now what is the double?
Oh, wait. What is the asterisk thing?
Yeah, the double asterisk.
Oh, yeah. Oh, okay. So it's essentially the union of an arrow with an arrow. So it's just like two arrows next to each other. But I didn't want to write arrows, so I just wrote an asterisk. Yeah. It's a two-element set. Yeah. Yeah. But the point is, it's not empty. It's not the empty set. Yeah. Okay, good. So this is nice, but it's certainly not everything because we haven't even gotten to probabilities now. So what does that look like? I mean, you just basically have zeros or ones. It's like binary, which is okay. But what you'd really like is if you had this sort of column vector where these numbers were something like conditional probabilities. So like, what's the probability that I'll see small blue given blue? I don't know, 0.75. So you'd like to have something that looks like this. And the point is that the sort of 2.0 version of category theory, enriched category theory, allows us to incorporate these in a way that I think is nice. So I'm going to try to explain this again from a high level. Now, in ordinary category, what we've seen so far, category theory, each pair of objects, x and y, have a set associated to them. The intuition to have for enriched category theory is that this set may not be a set. In other words, think of x and y as being vector spaces, and morphisms are linear transformations. So you can look at the set of linear transformations from x to y, but that's not just a set, because you can add 2 linear transformations and get another one. And you can scalar multiply a linear transformation to get another one. So in fact, you don't just have a set, you have a vector space worth of linear transformations. So in other words, this set is like more than a set. It has more structure. And so that's kind of the idea. In enriched category theory, each pair of objects has associated to it another object in some sufficiently nice category, where sufficiently nice means so that you can write down axioms that are analogous to the ones from ordinary category theory. But the point is, this subsumes the definition on the left. I mean, this subsumes the idea on the left, because it turns out that an example of a sufficiently nice category is the category of sets. So you kind of generalize your definition to include the usual case, but to also have more. Now, what's really nice is that another example of a sufficiently nice category is actually the unit interval. So remember that example we saw earlier? The objects are just the numbers between 0 and 1, and the relationship is just the usual order. So this turns out to be very nice. I mean, it has what's called a monoidal product, so you can multiply numbers together. It also has all limits and co-limits, so these end up being the min and max of numbers. So it's a very nice category. It has a lot of structure. So basically, everything we could do with sets, category theory over sets, we can now do category theory over the unit interval. So I'm going to show you another slide. I didn't need to include this, but I just really want us to appreciate how nice all of this works out. So here's just the loose definition of an enriched category. So I'm just kind of summarizing now what I said on the previous slide. Given a sufficiently nice category, you call this V. A V-enriched category C has objects like before, and here's the difference. You have now an object in your other nice category. Maybe this is vector spaces, maybe it's set, maybe it's the unit interval. Together with something like a composition rule. So you write down something that says, given an object corresponding to x and y, given an object corresponding to y and z, there's a way to map from those to an object corresponding to x to z. So you can't really think of the, what's comprising this blue blob. You don't really want to think of them as morphisms now, but sometimes it's helpful to do that. Anyway, you could ignore this. Here's the point. Here's what we want in the case of language. We are interested in the case, as I said, when the base category is the unit interval. Our objects, again, are strings from some finite alphabet. We want something like a probability of continuation, which again, I haven't really specified, but I'm going to get there in just a second. And to motivate how to understand this pi of y given x, it helps for us to think about this composition rule. And that was the question mark I said earlier. What does this even mean here? And do we have this in language? Well, the answer is yes, if you want to think about large language models concretely. So everything I've said is just kind of theory. I didn't say fix a model. Yeah.
Can you go back? Why is that not true by definition of probability? Because the sum over y of the left-hand side equals the right-hand side. I don't need to think about LLMs or anything.
Well, I haven't really said what does this mean. I mean, there's the question of does y contain...
Doesn't matter. That inequality is a theorem of trivial probability theory. Yes, that's true, always.
That bar does not mean conditional probability.
Yeah,
It hasn't defined what it means yet.
Yeah, I haven't defined what
supposed to be
that pi of y given x is not
It's not conditional probability, no.
It's supposed to intuitively be that.
Yeah, it's intuitively. So that's kind of my comment at the beginning. We're not really specifying, but it's something like you have some intuition that there is a number that's like a conditional probability, but I haven't specified what it is. I'm going to right now, though.
Okay, why not? Okay, so you don't want it to be a conditional probability.
No,
Okay.
yeah. But if I think about having a large language model, I can now think of the conditional probability distribution generated by that model. So in other words, for any prompt, x, your LLM gives a probability distribution, a literal conditional distribution, P of blank comma X on the set of tokens, let's say. And so these probabilities multiply now in the normal sense. So if I have a prompt, say X1, I feed it into the model, I get a distribution on all the possible tokens next. Let's say I select X2. So I now see the string X1, X2 with probability P of X1, X2 given that I fed in X1. So then I take that output and then I can feed it back into the model and then I sample again. It chooses a token, say X3. So I see that string with this probability conditioned on the fact that I fed in X1, X2 there. So I'm like sampling, kind of like taking my strings, feeding it back in, taking my strings. So then the probability of that two-step process is just a product of the intermediate probabilities. So now, if I just think in general, I have a string X, and I think of Y now. Now, this is going to answer the question that you had earlier. If I think of Y in this case as extending X by adding one token on the right, and I think of Z now as extending Y by one token on the right, then I can think of this probability, and this probability of Z given X is exactly the product of the intermediate ones. Yeah. And so this observation now prompts us to now define what this symbol means. So I can define pi of Y given X to be just the product of these successive probabilities if Y is contained in X in this way. I'm generating one token at a time. If X and Y are equal, I'm going to define pi of Y given X to be 1. And I do that so that the category theory works out nicely. If X is not contained in Y, I'm going to define this to be 0.
So just to make sure I'm tracking, the answer to the question I asked was yes, it's always true. But you're now showing it, and here's a particular example. I'm defining probabilities this way. But you can define them any way you wanted. And that would still be the associative rule would still work.
Yeah. So that's, you can think of it that way. And here, this is nice because you get equality. I guess you get it there too, but yeah. I will say in our original, in the paper that I mentioned at the beginning of the talk, we don't specify where the probabilities come from. We just sort of say, suppose, in other words, we don't mention anything about language models in this sense. But I do want to give a hat tip to Juan Pablo Vigno, who's a mathematician at Caltech who recently made this observation about just having a language model. Yeah.
So from blue to thin blue would be 0?
From blue to thin blue. Okay, so caveat. This definition, I swept this under the rug. Thank you for asking. This definition works if you adjust your category slightly and you say there exists an arrow from X to Y whenever Y extends X on the right. So I haven't really thought about how to say this if like your blue fits in the middle of a string or if it's on the, because LLMs go forward. So I totally I switched on all of us on this slide. Yeah, thank you. So from this perspective, though, you now have a way to associate an object in the unit interval to a pair of strings, in this perspective, that satisfies the composition rule. So when you write this out, you get this for all strings. And so the punchline is when you sort of recall the definition of an enriched category on a few slides ago, you can now think of language or strings in language as a category enriched over the unit interval. Before I called our unenriched version like L, sans serif L, but now we can view this enriched version as a script L. Was there a question in the back?
So this definition allows for, that doesn't define a pi uniquely?
Here I'm defining pi in terms of the probabilities given to you by a language model.
Right, and I guess it's guaranteed to give the same probability for different paths between two words. Between two strings.
No, because I guess a path between strings, if I have like x1, x2, x3, and x1, x7, x3, there's going to be different probabilities associated to each of those. Potentially, because...
But they should be equal, right? Because there's at most one morphism between any two objects.
Yeah, okay. So the two strings I just mentioned are not the same because, presumably x2 is not equal to x7. But yes, there's at most one string, there's at most one arrow between any two objects in your category. So there's at most one number, yeah, or there's always one. There's at most one non-zero number, unless it's one, then there's, okay, anyway, yeah.
I don't know if this is, I'm assuming you're not worried here about tokenization issues. This
No.
is not like, okay, yeah, I don't know if
Oh, I
this
don't know
is-
if his
this
question
goes
is
there.
related to that, but
But,
I haven't said anything about, yeah.
Because, I mean, like issues of having the same string be expressible by multiple tokens, and this is not like
No, no,
yeah,
no,
okay.
no.
I don't know if this is what was worrisome there, but okay.
Yeah, sorry, thank you.
Yeah, good, thanks for clarifying, yeah. Okay, so just because of time, I just want to quickly speed through the rest. So now we filled in the question mark that we had earlier. We have this nice composition rule, so language fits very nicely into not just ordinary category theory, but also enriched category theory. So I'm just going to be really quick now. I mentioned the mathematics is such that you can, it's almost like Mad Libs, you know the game of Mad Libs, you like just swap out words for other words and get the same story. So by swapping out the category sets for the unit interval, you can basically repeat this idea of representing meanings by functors and the operations limits and colimits. All of those ideas have enriched analogs. And so I'm not going to spend a lot of time. I'll just kind of tell you the end of the story there. So you can consider now enriched functors. So these are like functors, but you got to modify it a little bit. But the idea is the same, associated to expressions. So there's enriched versions of representable functors associated to a word like blue. And you get exactly what I said earlier. Essentially, the output of this functor looks like a column vector indexed by strings, where the entries now are these pi conditional probabilities, so to speak, that we saw earlier. So that's nice. And again, enriched category theory gives you enriched analogs of ways to combine objects. So now we can combine our functors using what are called weighted limits and weighted colimits. So these are the enriched analogs. The definitions, again, are not really worth showing. But the point is, if I take the enriched functor associated to red, I do the enriched version of disjunction or coproduct with the representable functor associated to blue, I get a column vector, again indexed by strings. And now here, this is interesting, I think. The values that you get are the max of the value of the two functors individually. Why is it max? Well, it turns out that the coproduct in the union, like disjoint union, in the unit interval is the maximum of two numbers. So you're kind of computing this pointwise, and you're using the categorical structure in the unit interval.
What about intersection then?
Yeah, it's going to be the min. Yeah. Yeah. Okay, so.
Intersection is mean, not 1 minus. It reminds me of many-valued logic.
Oh, yeah.
You don't do straight mean.
No, it's just min, and that's because all limits and colimits in the unit interval are just the meet and join. It's just min or max.
This is probabilistic logic, because it's not. And it's not also a many-valued logic because of probabilities, right?
Yeah. I think there should be a connection, and I don't know it. Yeah, maybe we should
Or
talk.
enriched categorical semantics for many
Yeah. I would like to learn more. I think there's definitely a lot more here. But okay, just for the sake of time, let me just say now, just to wrap up, that you can think about probabilities, or you can think more geometrically if you like. And that's because the negative log provides a mapping from the unit interval into the extended non-negative reals. So in other words, I can actually think now of the distance between two strings as the negative log of this pi between them. It's a distance because, well, I'll say this in a second, but intuitively, what you get here is that likely continuations of blue are close to blue. And we can define the distance from x to y to be 0 if y is not a continuation of x. So something like curiosity killed the cat is infinitely far away. The distance is infinity. So this is a nice interpretation. And you can repeat the story over again. So I mentioned distances I mean, it's really a metric. Actually, this is a metric, except you don't have symmetry. So the distance from x to y is not necessarily the distance from y to x. So a category enriched over 0 to infinity is sometimes called a generalized metric space. It's not a metric space, it doesn't have symmetry. But the point is, just like you can repeat the whole story for the unit interval, you can repeat the whole story again for extended non-negative reals. You can get these representable functors now in terms of distances, so your column vectors are now valued in 0 to infinity. You can now compute these limits and co-limits of these representable functors. If you like to think from a geometric perspective, you can think of like the distances between the meaning representation of different strings, and maybe that gives some insight. One example, just really quickly, so Yannis Vlasopoulos, who I mentioned earlier, together with Stefan Gobert, another mathematician, so they recently reinterpreted this generalized metric space of language in terms of tropical geometry. And so this is a recent paper on the archive, which I would recommend. So all I'll say is that they think of our 0 infinity category as now a polyhedron, where these representable functors are like extremal rays. So they're sort of the things that are generating this shape. So it's almost like our representable functors are building blocks for this larger semantic space of language. I would say if you're interested, you can take a look there. Another interesting avenue from a geometric perspective, so I mentioned Juan Pablo Vigneault earlier. So there is something in category theory called the magnitude of an enriched category. This is a numerical invariant. It sort of generalizes the Euler characteristic of a topological space, the cardinality of the set, the entropy of a probability distribution. So it's like a number attached to the thing you're interested in. Enriched categories that are equivalent have the same magnitude, so it's invariant. So when you think of language, our category as just extending strings by adding tokens on the right, and by the way, it's a caveat, this works for finite enriched categories. So if you only look at strings up to some fixed length, so things are finite. So Juan Pablo recently computed the magnitude of this category. Actually, if you think of sort of rescaling your metric space by parameter t, you get a magnitude function. So in this case, you end up, the function you get, for every string in your category, think of feeding that into your LLM as a prompt, right? So now you have this conditional distribution on tokens. Now for each of those strings, take the Salas entropy of that distribution and add them all up, and then scale by t-1. Why does that come out? Well, we're going to put this on the archive in a few weeks, so I would say take a look there. There's some interesting combinatorics there that Juan Pablo worked out, so that's kind of where that comes from. And then I think the last sort of thing I'll say in the array of things that come out from this perspective, I'll conclude by bringing us in the following way. To compute this magnitude function, it's actually quite simple. Consider a matrix indexed by your strings. Now, the xy entry is the exponential of the distance between x and y, but with a t there, negative exponential. Okay, so you have this matrix. If this matrix is invertible, you can take the sum of all of the entries of the inverse matrix. And this is actually where this comes from. So the definition is very simple. Working this out is a little bit, that's where the work comes from. So I'm just mentioning that because there's other things you can do with matrices, of course. Instead of indexing by strings, you may be interested in like words from a corpus of text or something, and you have a matrix indexed by different words. You can maybe consider entries that are like pointwise mutual information or something that tells you about how the words are used. And you can do something else like compute SVD and get something like word embeddings. That's something you can do. Another thing you might want to do with a matrix is maybe like choose a threshold value and set everything above that 1 and everything below that 0. So you get a binary matrix. Now, if you do something that's analogous to singular value decomposition, but it's a little outside the scope of linear algebra, but it's analogous. You get, that leads you into something called formal concept analysis, which you may know. It's like a little piece of lattice theory that allows you to have a concept hierarchy where you have pairings between objects and their attributes. So almost like pairings between left and right singular vectors, you get pairings between objects and attributes, or in the case of language, something that feels a little bit like concepts that are inherent in your words. The interesting thing is that the framework that you use to work all of this out is, again, a special case of a construction, not just in category theory, but in enriched category theory. And that's called the Isbell completion of something called a profunctor, which is the category theoretical version of a matrix. So it's really interesting that you can kind of, again, like, crank the handle and see what you get out of it, and that it corresponds to things that folks are already thinking about. So what I've mentioned there, I won't go into for the sake of time, but I'll say we've written about this. This is with Juan Luis Gastaldi, who is a philosopher at ETH in Zurich, along with John Turilla, who I mentioned earlier. This came out in the notices of the AMS earlier this year, and so more information is there. But I think I'll stop there. So thank you.